All right, our next topic in chapter 16 is solubility equilibria. We're going to move away from acids and bases and pH here for a little bit and talk about salts that are generally considered to be insoluble. So all ionic compounds are going to dissolve in water to some degree. We classify some of them as insoluble, but in reality, they're very slightly dissolving. So we're going to look at the equilibrium associated with that. So the equilibrium constant associated with salts dissolving in water is called KSP, or solubility product. The KSP is simply because your insoluble salt is in solid form, you don't have to worry about the denominator, the reactants part. So your KSP is simply the ion concentrations multiplied by each other. You can see that these KSPs for generally insoluble things range from the 10 to the minus 5 range all the way down to 10 to the minus 36. They can be very small. Molar solubility is the amount of solute that will dissolve in a given amount of solution at a particular temperature. So the mole of solubility is the number in moles of solute that will dissolve in a liter of solution. It's the molarity of the saturated solution. So we're going to just look at an example because I really think that's the easiest way to do this. So calculate the molar solubility. Now, when we're looking at things like ice tables, the molar solubility is your X value. Here we're going to be using the letter S to represent it for solubility, but that's what you're looking for of lead 2 chloride in pure water at 25 degrees Celsius. So here we can write our KSP expression. Our KSP is going to be our concentration of lead times our concentration of chloride squared. Here we have to pay more attention to our coefficients again. We didn't have very many coefficients in the acid-base portion. Pay attention again there. Then our initial, we're starting at 0. Our change, we're gaining S in our lead, 2S in our chloride because we get 2 of them for every unit dissolved. So at equilibrium, we have S and 2S. So we can plug that into our KSP expression. Our KSP is equal to S times 2S squared, or KSP is equal to 4S cubed. So 2 squared is 4, S squared times S is S cubed. Then here's that worked out for you. Then you can look up KSP from the table. There's KSP equals 4S cubed. If you look KSP up for lead 2 chloride in the table, it's 1.17 times 10 to the minus 5th. So I can plug that in for KSP and solve for S. And so my molar solubility is 1.43 times 10 to the minus 2 molar. Yeah, these questions, the key to them seems to be remembering the coefficients and that they go in both the change and as an exponent. And then remembering that when it's asking for molar solubility, you're looking for the S or the X value. When it's looking for the equilibrium solubility product, that's going to be your KSP value. So here's one where we're working backwards. Determine the KSP of lead 2 bromide if its molar solubility in water at 25 degrees Celsius is 1.05 times 10 to the minus 2. So we have PbBr2 in equilibrium with lead 2 plus 2 bromides. We know that our KSP is going to be our lead times our bromide squared. For my ice table, starting with 0 plus S plus 2S And then I know from my question that my S is 1.05 times 10 to the minus 2. So my KSP is going to be, plug this in, S 2S squared, or 4S cubed again. And then if I take 4, my S is 1.05 times 10 to the minus 2, and cube that, I can find that my KSP is equal to 4.63 times 10 to the minus 6. Now remember that molar solubility is related to KSP, but you can't directly compare solubility by comparing KSPs because of the stoichiometry involved. So if we look at our calcium sulfate here, we have a KSP of 7 times 10 to the minus 5, but if I solve for my molar solubility, my KSP is going to be calcium times SO4, which if I did an ice table, it would just be S times S. So my molar solubility here is just going to be the square root of 7.10 times 10 to the minus 5, which is 8.43 times 10 to the minus 3. So 8.43 times 10 to the minus 3 compared to 1.05 times 10 to the minus 2, even though the KSP here is smaller, my is larger, sorry, times 10 to the minus 5, my solubility is smaller because of the number of particles dissociating.